Duchy of Cornwall, in the far southwest corner of England, is one of the oldest tin mining areas in the world. Today, most of the mines are derelict, and the countryside is scarred with the remains of the old pithead workings. The tall buildings, which once housed the mine pumping engines, are a part of the Cornish landscape. Most of the engines are broken up and scattered. There are still a few Cornish pumping engines working today. These giant machines were designed and built in the 19th century by Cornish engineers. Massive construction of the parts and sound design are two of the reasons why engines such as these are still working. They were in their day the most powerful and economical steam pumps in the world. Standing beside modern headgear, they remain as a monument to steam power in the 19th century. The Cornish pumping engine has been an essential part of the Cornish mining industry for over 100 years. It has made it possible for the miners to work safely underground and to win great quantities of rich ore, tin, copper, arsenic, and wolfram. Mineral wealth from deep workings which would be rapidly flooded if the great engines stopped. The more recent open workings of the China clay industry must also be kept clear of water, as high-pressure water jets are used to wash out the clay from the decomposed granite in the pit. The mixture of clay and water is then pumped up to the surface. From here, it flows away for treatment. The development of these great steam pumps in Cornwall has therefore been an important factor, not only in deep mining, but in the surface workings of the China clay industry. The first ideas for the beam pumping engine arose from quite simple principles. In a hand pump, the plunger is raised and lowered by a lever, which works on a pivot. To pump the larger quantities of water that accumulate in the mines, a bigger pump handle, the beam or bob, is used. The pump plunger becomes the main rod. This great wooden pumping rod extends 2,000 feet to the bottom of the mine shaft. It weighs over 100 tons, and as it is so heavy, some of its weight is counteracted by a balance bob loaded at its outer end. Sufficient weight remains to cause the rod to descend by gravity, thus pumping the water up to the surface. To raise the great rod, a powerful engine is needed to pull down the other end of the beam. This is what the Cornish engine does. It lifts the great rod, which then descends by its own weight, pulling the piston back to the top of its stroke. discovery of the way to use steam to give this power is a part of engineering history. Let us go back into the past and see how it all began. In the early 16th century, miners began to sink shafts into the earth. Water seeped into their workings, and raising it became, in time, their greatest problem. Their primitive machines were unequal to the task. In the 17th century, an intensive search was made for a new power which would raise water from the mines. The philosophers began to see that capabilities useful for this purpose were possessed by steam. By boiling water in a closed vessel, steam could exert pressure. This pressure could force water up a pipe. These facts were first published in 1615. But even before this, it was known that if steam were allowed to cool in a closed vessel, it condensed and left a vacuum. Water could be raised by allowing the weight of the atmosphere to force it up into the vacuum. These principles of pressure and vacuum were first applied practically by Captain Thomas Savery in 1698. By condensing steam alternately in the two vessels on the left, water was sucked up from below. Steam pressure then forced the water upwards. But even in their simplest form, these pumping engines were dangerous to work because the boilers could not be made strong enough to resist bursting. Savery had hoped to use his fire engines for the fountains which were so popular during the late Renaissance. He also planned to use them in the mines and to pump London's drinking water from the Thames. But his engine was ahead of its time and did not develop. 8 years before Savery patented his engine, Papin, a French philosopher, had unwittingly given the clue to a successful pumping engine. He made a small metal cylinder and piston. A little water was introduced below the piston. This water was then boiled. The steam pressure forced the piston up. The piston was then held up by a catch. As the cylinder cooled, the steam condensed, leaving a vacuum under the piston. When the catch was removed, the weight of the atmosphere forced the piston down. Papin was the first to produce a vacuum by condensing steam under a piston, but he did not follow up his idea. 20 years later, the idea was taken up again. A successful cylinder and piston engine using vacuum only was built by a Devonshire ironmonger, Thomas Newcomen. As the weight of the pump rods swung the beam, the piston was pulled up. The top of the cylinder was open to the air, and the bottom was connected to a boiler. Low-pressure steam from the boiler entered the cylinder as the piston rose. A valve at the bottom of the cylinder was then closed, and the pressure of steam below the piston and the pressure of the atmosphere outside were now about equal. Cold water was then injected into the steam, which condensed. The weight of the atmosphere forced the piston down. The steam was once again admitted to the cylinder, and the condensed water in the cylinder blown out. The piston was again pulled to the top of its stroke by the weight of the pump rods, and the cycle repeated. These engines were called atmospheric engines. This is a model of such an engine built in France in 1735. Here we see the open cylinder top, and below the water jet to the left of the steam pipe to the boiler. The simple lever system on the left operated the valves. Apart from the clock, this was the first machine to work itself. Although these atmospheric engines worked quite well, they wasted fuel. With each stroke, the water jet cooled the cylinder, which then had to be reheated with boiler steam. But the engines were soon pumping in Cornwall and in many other parts of Britain. Most of them were used to drain water from the mines in the coal fields, where fuel for the engines was plentiful and cheap. But there was no local coal supply in Cornwall. The fuel for the mine engines had to be transported long distances from South Wales. Thus, in Cornwall, there was an incentive to keep down pumping costs by making better engines. By 1772, John Smeaton had doubled the efficiency of the atmospheric engine, which remained in use long after Newcomen's death. The next great step forward in the history of steam began in 1763, when this little model of an atmospheric engine came into the hands of James Watt, a young Glasgow instrument maker. His experiments with it disclosed some fundamental facts about heat energy and led him to design a new engine. This engine was at least 4 times as efficient as the best atmospheric pumping engines. Instead of placing the water jet under the piston and so cooling the whole cylinder, Watt condensed the steam in a separate vessel. This condenser was the greatest single improvement ever made in the steam engine. It consisted of a small pump and a hollow vessel immersed in cooling water. A pipe ran from the vessel to the engine cylinder. A valve, the exhaust valve, controlled this passage to the condenser. When the valve opened, the steam passed down the pipe into the condenser, where it met a jet of cold water. In a very short time, all the steam condensed, and a vacuum was formed without cooling the main cylinder with the water jet. As the engine made its stroke, the small pump removed surplus water and air from the condenser. The vacuum, once established, remained. Thus, the steam condensed in an instant when the exhaust valve opened. Watt also enclosed his cylinder in an outer casing. This casing was filled with low-pressure steam from a boiler. Thus, the cylinder and piston were kept hot all the time. By steam pressure above the piston and vacuum beneath, the piston was forced down. When the 2 valves closed at the bottom of the stroke, the piston was held down by the steam pressure above. A pipe connected the space above the piston to the space beneath and was controlled by a valve, the equilibrium valve. The pressure of the steam on each side of the piston was equalized when this valve opened. The piston could then be pulled up until the equilibrium valve closed. The steam below the piston was then condensed for the next vacuum. Steam was again admitted above the piston, and the cycle repeated. Valves close, Piston is held until the equilibrium valve opens. Equilibrium valve closes. This is a model of old Bess, Watt's first successful engine. She was built in 1776 and used to pump water up to a channel to drive a water wheel. This was a cumbersome way of converting up and down or reciprocating motion into round and round or circular motion, and Watt later developed the first successful rotative steam engine. This was used for mine winding and for mill driving, and greatly enlarged the scope of steam power in all parts of the world. But the up and down motion was still essential for pumping. Watt's engines took the place of the atmospheric engines, which had been in the Cornish mines for over half a century. But as the mines deepened, the cost of coal again became a problem. Still more power had to be achieved from even less coal if the mines were to pay their way. The answer to this problem was to use high-pressure steam. The Cornishman Richard Trevithick is given the credit for developing its use. In about 1812, he brought out the cylindrical Cornish boiler. Made of riveted wrought iron plates, it was strong enough to resist steam at high pressures.
I think, with the advantage of this fireplace, we will make a great saving. The new engine will work with steam at about 25 pounds to the inch. It is not intended to alter any part of Mr. Watt's engine and condenser, only to cut off the steam at about a third stroke and let expansion do the rest of the work.
This use of high-pressure steam to give extra work was known to Watt, but it rested with the Cornish engineers to make it safe to use. By 1835, steam pressures had increased tenfold. The Cornish engine was 4 times as efficient as the best Watt engine. 16 times better than the first atmospheric engine built by Newcomen. By 1850, the engine had become almost standardized. This model shows how the engine was arranged in the house. The cylinder and valves on the middle and lower floors, with the valve gear, in the basement and outside, the exhaust pipe, condenser, and air pump. And above everything, on the top floor, the beam. In order to see how the parts of the Cornish pumping engine work together, let us look more closely at this representative engine in Cornwall. Because the end of the beam attached to the piston rod moves in the arc of a circle, this parallel motion, invented by James Watt, keeps the piston rod vertical during its travel. At the top of the cylinder, 3 valves are grouped together. The nearest valve is the steam governor, which regulates the supply of steam to the center valve, the steam inlet. Furthest away is the equilibrium valve, or Uncle Abram, as the Cornish engineers nicknamed it. These are two of the valves which concern us. Steam inlet on the right and equilibrium. At the bottom of the cylinder is the exhaust valve. The steam below the piston passes into the condenser when this valve opens. Steam is then admitted above the piston for part of the stroke. Finally, the equilibrium valve opens for the upstroke. That is the Cornish cycle. Vacuum, high pressure steam and cut-off, equilibrium. The valves are closed by the rod behind them. This is called the plug rod and is worked from the main beam. As it moves up and down, it pushes handles connected to the valves. It will be easier to see how this gear operates if we stop the engine and then put it to work. While the steam is being cut off, the piston is pulled to the top of its stroke by the weight of the pump rod outdoors. This is the position of rest for the engine. To pull down the beam again, the exhaust valve must first be opened. The steam valve is then held open by hand and the regulator opened, thus admitting steam above the piston. As the plug rod descends, it closes the exhaust valve by pushing down the bottom handle. Near the top, the plug rod closes the equilibrium valve and the piston again pauses. The cycle is then repeated. When the condenser vacuum has been fully built up, the strokes are faster and the pauses are reduced. Finally, the engine can be left to run itself. The steam to the cylinder is automatically cut off at 1/3 stroke by these levers, which control the steam inlet valve. They close the valve when the slide on the plug rod pushes them down. The mechanism which opens the valves was designed by James Watt, the use of specially timed catches on the valve controls. The exhaust valve opens when this catch is released. And when the plug rod closes the valve, it also cocks it. Below the floor is the mechanism which times the release of the catches and the opening of the valve. This is called the cataract. It consists of a small cylinder full of water and a weighted piston. As this sinks, it slowly forces the water out of the cylinder. The piston is connected to the catches, which are slowly raised. The plug rod resets the cataract and the cycle is repeated. Thus, by the use of this mechanism, it is possible to time accurately the number of strokes per minute and the length of the pauses between the strokes. The Cornish steam cycle was later applied to the rotative engine. This small engine is used for pumping. The rod linkage conveys the power to the pump rod in the shaft. The valves must be timed entirely by the engine itself, as it cannot pause at the top or bottom of its stroke. The piston is pulled to the top of its stroke by the weight of the cast iron connecting rod at the outdoor end of the beam. This rod weighs 3 tons. The gearing transmits the power to the drive shaft. The condenser and air pump are essentially the same as Watt's original invention. The economy of the Cornish pumping engines ensured the 19th century prosperity of Cornish mining. At every Cornish pithead, there arose the characteristic form of the granite pumping engine house, with its circular chimney topped with bricks. The news of this success spread abroad. Cornish engines began to be erected in many other parts of Britain. This Cornish engine, for example, only stopped work in 1946. It was made in Cornwall and erected in London for pumping part of the city water supply. Soon they were pumping in countries as far apart as Australia and Russia. But few were working today. Here, in Holland, is a pumping engine built in 1849, now preserved by the Dutch as a technical monument. The building and the 8 pumps were designed and built by Dutchmen, and the engine was designed and made in Cornwall. These engines worked for 84 years to keep the land dry and arable. All the 8 pumping beams are connected to a single piston rod. The great cylinder is 12 feet in diameter, the largest ever built. Here is the cylinder after casting in Cornwall, with the men who saw to its construction. Jabez Bickle was one of a great company of Cornish craftsmen who played their part in developing the work begun by the pioneers of steam power. There was Denis Papin, who first condensed steam in a cylinder. Thomas Savery, and the first pumping engine to work. Thomas Newcomen, and his atmospheric engine. James Watt and his great invention of the separate condenser. And the Cornishman Richard Trevithick, who made practical the use of high-pressure steam by introducing the Cornish boiler. To the work of these pioneers, we owe the development of the great machines which came to be known as the Cornish pumping engine.